Hello everyone, my name is Yuanzhe. I'm a PhD student at the University of Oxford. Today, I'm pleased to give a presentation entitled Radial Icicle Tree, Node Separation and Area Consistency. It is a new visual representation that transforms the rectangular boundary box of an icicle tree into a circular sector while introducing gaps between nodes and maintaining area consistency for nodes of the same size. Before discussing the new design, we need to identify the weakness of current designs. Start from an icicle tree. In this icicle tree sample, the same nodes in value 0.5 are quite difficult to notice. In this icicle tree sample, we illustrate the situation where two nodes appear merged into one. The merged nodes refer to the difficulty distinguishing nodes of the same class, which are usually depicted in the same color. In the slide, the deep green color shows some parts belonging to the red section and some to the blue section. But it is not easy to find the same color belonging to the different further sections. For some bus tree plots, there is a problem of size inconsistency. The size inconsistency means nodes with the same values are shown in different sizes. In the slide, the blue node with the same value in the second layer is bigger than the blue node one in the third layer, even though their value is the same. In fact, multiple weaknesses can be found in these two types of the tree plots. These problems appear in the same figure and make users difficult to discover the information from their data. To solve these three issues in the sunbus tree and the icicle tree plots, RIT introduces gaps between sections by cutting wedges and adding top-up areas. This solves the potential problems of seeing merged and inconsistent size nodes. In this slide, we briefly introduce the major designs considered in our design process. To solve the thin node issue, we try to transform the plot to polar coordinates to gain more space, as the circumference is longer than the width. Then we try to add the large gap potentially to ensure the area consistency. Instead of reducing the angle of each angle sector, another remedy may be to reduce the height of each of the sections. To control more precisely, the wedge that is cut away and the top-up that is added, it needs to be explored mathematically. For generating a RIT plot, specifically, we first draw a new layer on a root node, then cut away one end, and then cut away another end. The size of the cut depends on the proportion of the node itself. The proportion of the cut part will be larger if the proportion of the node itself is larger. Since the cut-off part is not exactly equal to the change in the height of the layer, we need to add a top-up layer to control the height of the new layer of the RIT. The height of the top-up can be calculated by the following formula. We can see that the height of the top-up layer depends on the width of the inner circle as well as on the angle of the cut-off edges and the proportion of the nodes. In other words, the top-up layer is in fact different from the node to node, so it is not possible to set the top-up layer to be the uniformly to all the nodes. Based on the understanding of the top-up layer, we continue to draw more RIT layers, or in other words, we repeat the previous steps. For each node, child node, first we draw the layer, then cut one end, and then cut another, and finally adding the top-up. We repeat the steps until the completion. In summary, we use a cut and top-up strategy to remove a wedge from a section, and then add a small top-up to maintain consistency with across layers. We demonstrate through mathematical calculation the optical gaps to maintain visual consistency across layers. The more details can be found in the paper. By setting different radii and layer widths, we can generate variations of the shape from icicle tree to some bus tree plots. A typical change is from an icicle tree into RIT, or from a sunburst tree into a donut-shaped RIT. In fact, we can also make the change directly. By adjusting different control parameters, RIT can also be used to plot from icicle tree to sunburst tree plots. Beyond the shape variations, we explore the scalability of the RIT plot algorithm. We present 6 samples of the tested trees with more samples available in the paper's appendices. We also explore the complexity of the RIT plot algorithm, as shown in the figure. It suggests that the runtime complexity of the algorithm is O(n), where n is the total number of the nodes. In other words, the result of a scalability test evidence that the RIT algorithm is linearly scalable about the total number of the nodes in a tree. More details about the scalability testing can be found in the appendix. In this paper summary, we introduced a novel visual design called the Radial Icicle tree. This design addresses the limitation related to node separation and area consistency found in the existing designs. We show our design idea by editing its mathematical properties and computational technology for achieving optimal node separation and area consistency. We present a recursive algorithm for plotting RIT, and our experiments demonstrate its linear scalability. We also test the plot in synthetic data and public datasets. The open source RIT code is available on the GitHub repository in the following link. There is an acknowledgement of appreciation for the support. Thank you for listening to my presentation. I truly appreciate your engagement and interest in the topic.